Hi, everyone, and welcome to another mock interview with Exponent. Today, we are here with Suman. Suman, would you like to introduce yourself?
Hi everyone, I'm Suman Bukha. I'm a senior manager at Smartship. I've been coaching for last 2 years and on several aspects like system design and coding as well as engineering leadership. I'm excited to do a mock with you here.
Fantastic. Thanks for being here, Suman. So, my question for you today, I would like you to design the backend system for a weather app.
Definitely. So let's get started on that. So the weather app is an important one in nowadays. Like if you want to plan your day, if you want to plan for the weekend, it's always good to know how the weather is. If it's sunny, it's gonna be cold or so. Based on that, you can plan your activities. So I'll make some assumptions and also go through certain aspects, and then feel free to stop me anywhere or ask me to dig deeper into the things.
Sure.
And yeah, so as we were talking about, weather application is quite important nowadays. So let's look at like what is a typical success criteria looks like. So one of the thing everybody will look for is like accuracy of the weather. So if it is sunny, you want it to be knowing it's sunny, and also it has an ability to predict the weather a little better so that you can plan activities accordingly. So for the weather app, what we would be looking at today is making sure that accuracy of the weather information is critical. And then the timeliness. So you want the weather information to be accurate, and also you want it to be latest as well. So as much as information you can gather and then provide, that will be great. And as the system gets popular, you have a lot of users who will be using this. So the system should scale, and also it should be fast. Everything has to be faster nowadays, so you want this app to be performing really fast, no matter whether you're looking at current weather or past weather or future weather, right?
When you say fast, do you mean the actual responsiveness of the application, or do you mean how fast we update the information?
A bit of both, actually. So I would say like how fast the information comes in. Like think about if it is taking a couple of minutes to load the information and then show it, people may not be excited to check whether in that particular app they might actually look for some other things.
Okay.
Yeah, let's get into some of the functional requirements. As we were talking about some of the expectations for this particular service, making sure that we have accurate information, timeliness, scale, and performance. Let's look at the functionality point of view. In order to get the accuracy and timeliness, let's make some assumptions. So the first thing is like the weather data can be sourced from a weather company, national weather also. Otherwise, like let's assume for this particular case, we have sensors deployed all over the place, and then these sensors are directly communicating with the backend server and providing information. And let's say these sensors could be of different various features it can have. So let's say these sensors are providing data points like temperature, and then let's say humidity, as well as air quality. And then nowadays it's becoming critical to look at wind speed as well, because if you want to go for kayaking or so, it's always good to know how the wind and situation is. And other important thing is like let's say pollen index. These are the kind of things, and we can add some additional data points later point of the time, but let's focus on these are the few. And let's assume that these sensors are providing the information continuously. And that's an assumption, and there's a different team which will take care of deploying the sensors and connecting it to the backend service. We'll discuss a little bit how that connection would be and what information would be coming in. And the application should provide three different things for a given location. For a location, it needs to provide what is the current weather, and then it should also able to say what is the forecast for that specific location. And the other thing is sometimes you tend to look at the past weather information, so it should have features to show past weather information as well. So these are the three different aspects we will be focusing on, and we can add some additional functionality later, but as of now we'll only keep it minimal and then look for extension depending upon the time.
Okay.
Right. Anything else you would like me to emphasize on the functional requirements?
I think this is a good start. Let's
Okay,
dive in.
cool. So let's get into some of the non-functional requirements. So non-functional requirements mainly, we are expecting the service to be highly available. So making sure that this service is available whenever the customers are looking at it's middle of the night or in the middle of the day, whatever the time it is. But this is not really a financial or very critical system. So we are expecting maybe 999 availability. And in the beginning, we said like it should be performance, so low latency is an important thing. So let's say around 150 milliseconds of response for each of the API is something which you're expecting. You're not considering how much time the front end takes and all of those stuff. So front end is not in the scope of this design for today. Then we are sourcing this data from different sensors and processing and calculating certain things. But it could be giving little bit of different information if depending upon users querying it. It need not be highly consistent, but it should be eventually consistent, and we want to keep that window of inconsistency to as small as possible. So let's say eventual consistency is fine, and probably we will look at like maybe 1 to 2 minutes or so, and we'll discuss if time permits how what are the factors impacts those. And then another assumption we are making is this is going to be a global service, so everyone in the world should be able to access this and also use the data. You get the weather data from different locations. So from this, we'll jump into some of the back of envelope calculations. Okay, so there are two elements which are critical here. So we said like we have sensors which are pushing the data, giving the data, and then also we are saying like we have users who are requesting the data. So if we are doing the back of envelope calculation for throughput, let's say, we have to do this for do two different things. So the first one is sensors. So let's assume that we have maybe 100,000 sensors deployed all across the place, and then these sensors are providing the data points which we mentioned, and assume that all of these data points come as a single payload or so. Now 100k sensors are deployed, and how frequently these needs to provide the data. So we can assume that it may not be every second. We could configure in that way, but temperature doesn't change every second and humidity doesn't change every second. So basically, in this case, let's assume that maybe every 5 minutes we are getting a data point. So let me just scroll. Yeah. So every 5 minutes we are getting one data point. So that means like we are getting around 100k sensors by every 300 seconds, and in this way we will know what is the TPS we would be expecting from this. So in this case, what we are looking at roughly 300 RPS or TPS, you can say. So our assumption is these sensors are pushing this data at this rate.
Okay.
And then we are talking about user requests. So how many users would be there? How many requests would be there? Is it safe to assume, like, since it is a global service, we have, like, let's say roughly 100 million users on a daily basis?
I think that is, yeah, that's a good place to start.
Okay, sure. So, and let's assume that they are doing one query a day, so at an average. So in this case, you're talking about 100 million daily by 24 hours and 60 minutes and 60 seconds. So I'm just rounding up to 100k seconds, and then that will come up to 1000 RPS. And that's a uniform distribution over the day. And let's assume that at the peak time, like morning before you get out of the home or so, you'll be checking the temperature or the weather forecast or so. So in this case, like assume that instead of 1000, like let's say during the peak time, there is a 10x load. So that would be like 10k RPS. So that's a little heavy, and also looking at these numbers, sensors pushing the data, that's kind of a write operation, and then users requesting the data, that's like a read operation. And it's evident that this is basically a read heavy system.
Just to clarify what you wrote on that second line, so 100 million users daily,
Correct.
and you're dividing this by 100,000. Why that?
Yeah. So basically, if you are taking 24 hours a day and then 60 minutes and 60 seconds, this will come up to 84,600
Okay.
seconds. So I'm for simplicity, I'm just rounding up to 100K. And
Got it.
if you are very critical, we can say like it'll be 1.1
That's fine.
1100 RPS or 11K RPS at a peak load.
Got it. Okay.
Right? Yeah. So cool. Let's get into architecture. How does the architecture would look like for this system? So as we were talking about, assuming that we have sensors which will be emitting the data. So we have sensors which are
Mhm.
connecting to our backend service. Let's say I'm just drawing the first bare bones, and
Sure.
then after that we will go into some of the deep dive. And then we have a database which will be storing the information. And what we are assuming is we have the data coming in, and then data will be getting into the database. So that's the first part of the system. And second part of the system, what we are saying is like we have 10,000 user requests per second at peak.
Hmm.
So we would need a load balancer. Let's say we are putting a load balancer, and we have users who are actually using this system and who will be contacting our service through the load balancer, and then from it's coming to the backend. So a simple system would look like this, a very without diving into any components or anything.
Yeah.
But let's go into the deeper dive of this, and then what are the different things we need to think about. So what we said is like there are three different requirements we are talking about. One is that the users are getting the current temperature as well as forecast, and the third one is it's about the past weather information. And most of the times, people will be looking at current weather and the forecast as well together.
Yeah.
So let's assume that we divide into whenever we are returning the current weather, we will provide the current weather and the forecast for that day. And the rest of the forecast, like tomorrow and the next week and next 10 days or so, that will be a different service which will be providing. So that way we can divide the traffic into smaller and
Mhm.
specific segregatable components.
Yeah.
Now, what we do is like this backend service, what we said is current weather service. So that's basically our major backend service which will be providing the data. And then we said there will be forecast service which will be focusing on forecasting the information for rest of the week or later, like next month and stuff like that. It'll
Hmm.
also be dependent on the database, so we'll come to the breakdown of that. And then the other one is past weather. So we also said like there'll be some interest about like what was the past weather look like last month or last year or something like that. So that also will be looking at the database. And so as you're building these different components and looking at, one of the important thing to keep in mind is separation of responsibilities and single ownership responsibility. That's another thing you can think about. So as you see, there are three different services which are connecting to same database and then getting the
Hmm.
data. So a natural thing to do is basically you would divide this database into individual databases, and
Hmm.
then it'll have the relevant information for that particular service itself.
What's the advantage of doing that?
So imagine like the current weather is the one which gets the highest number of requests. So let's assume that we are getting out of 10,000, 8,000 requests are only for the current weather. So
Hmm.
now the forecast and past weather, sometimes they get starved in order to get the DB connection, if at all they're all pointing to the same database. And also, the advantage of that is you can actually have a larger database and this one have a smaller database because there's not that much of requests which are coming in. So
Okay.
those are the advantages. And also, whenever you're making changes to forecast database, you would not accidentally make any impact to current weather or past weather applications as well.
Okay.
So those are the things. And then let's go into a little bit into the other aspects of it, where when we said sensors are getting the data directly into the current weather, but that's not practical because considering how busy the current weather is, we want to make sure that the sensors are emitting the data in a different way. So let's assume that since these are IoT devices, we will be making use of some latest technologies like AWS IoT framework, and then it can pump the data into a different service where we have an API available, and then let's say, ingestion service, and then that service will take the information and then pump it into the database continuously. So that's one way we can actually do that. But as the data is coming into the current weather database, where what is the current weather for each of these locations, but
Hmm.
forecast needs to get that information as well. And what we want to focus on is how do we get that and what do we do. So this is where the data can come into, let's say, a kind of a data lake, which you can think of, because the data is a little bit need to be processed quite a bit, and also there will be different usage patterns for forecasting. And we are assuming that there is a forecast, let's say, LLM, which will be accessing the data from the data lake, and then it will be updating the forecast DB accordingly. So in this way, you
Question before we move ahead. So going back a little bit to you adding the AWS IoT and ingestion layers between sensors and database. Could you talk a little bit more about that? I think we glossed over that a little bit.
definitely. So basically, what happens is whenever if you are trying to do these sensors directly coming into the ingestion service or connecting to these things, you need to be able to deploy this service all over the world, and also like this service has to be available and also performant and support different uh, connection mechanisms or so. So here AWS has a framework which is AWS IoT. It's a service, and where it's specifically designed for IoT devices which
Hmm.
can connect to the AWS framework with
Hmm.
minimal work, and also they support quite a lot of different communication mechanisms, like it could be MQTT, it could be HTTP, or it could be web sockets as well. So all of
Yeah.
these will become easier for the development, and also it can scale quite easily. You can have ingestion service deployed maybe 3 or 4 different places
Okay.
in the world. You're not like
And
spreading it
so
out into thousands of locations or so.
got it. So what I'm trying to get at is what is the concrete advantage for the developer to have that service versus just having a direct connection between the sensors and the database?
One advantage is like simplicity, as I was talking about. So AWS IoT will keep it up to date, and also
Okay.
it'll take care of, it will provide you all of that information. Like if let's say one sensor is not providing you the data regularly, or the sensor
Hmm.
is providing some what do you say, garbled data or something like that. So it gives you different tools to play around, and also
Got it.
do some cross checks.
Okay, sounds good.
Cool. Let's go into a little bit of the past weather as well. So, similarly, how the data is coming in. So, the data is coming into the data lake, and from there, we can assume that the data will also be coming into this DB, and we can also keep some intermediate systems which will polish the data, or it will do some segregations or so. But right now, let's not deep dive into that in the interest of
Sure.
time. So let's focus on what kind of a databases would be ideal for these things.
Hmm.
So since we are talking about the data which is related to time, and it keeps changing over time. So by that, it kind of indicates that using some kind of a time series database would be ideal. So we have basically two choices, like either SQL or NoSQL, or relational, non-relational in a high level. And in this case, we established that this is not a financial system. It doesn't need highly transactional consistency or so. So in this case, like, and also considering the scale, it's good to choose a non-relational database. And depending upon the nature of this, for example, past weather, we are talking about different data points of the weather at different locations and different timestamps. So it's good to pick some time series database like InfluxDB also. Right. So let's say we are picking up time series for this, and in the forecast as well. Similarly, we can actually take all of these as time series databases.
Hmm.
It'll be uniform in what kind of a database types we are using, as well as it becomes easier to connect and then interact with each other. And is there any specific aspect you want me to focus a little bit more, Nima?
No, I'm curious to see where you're going.
Sure, definitely. So, and there are a few other things which we talked about. Is one thing is the sensors are emitting at around 300 requests per second, so the scale is pretty uniform, and that's fine. But let's say we are talking about the current weather application or current weather request that could spike quite a bit during the beginning of the day or during the middle of the day or so, or especially close to the weekends or so. People might be looking at forecast for the weekend and stuff like that. So there are two aspects where there could be sudden scale coming in. So one thing what we can think about is the current weather which is present. We can add some additional nodes, and also we can use either Kubernetes based solution where it can scale according to the load, and then it can provide the data as needed. But
Okay.
as you see, current weather is always getting the data from time series database and then returning the information.
Yeah.
But the data is only changing every 5 minutes. So it doesn't really need to go to the database that often. So what we could think of is adding some caches. So caches will reduce the querying time. Let's say, suppose there are certain areas like California. So there are a lot of requests coming in at some point of the time. We can cache that information, and we can actually be able to return that information quite fast. And that also helps with the scale as well as keeping the latency very low. But the other thing is, this information is kept there, and then it's working as a cache, which is close to the server. But we can also think about using some kind of other caches as well. So the other general cache which comes to mind is CDN. So in this case, suppose somebody is looking for the forecast for the weekend and it doesn't change quite a bit, and if somebody else is also requesting the current data or forecast, then we, instead of getting that request into forecast every time, we can actually have that information in the CDN, and then the users will also, the front end will automatically get the data from the CDN and then show it, so that the forecast service doesn't need to scale that much in the case of heavy load from a specific location, because CDN will take care of addressing all of the traffic.
Yeah.
So these are the two ways where you can scale your application really quick, adding some additional Kubernetes nodes or pods, and then also adding cache. It could be a Redis cache or Memcached or so. Otherwise, like adding a CDN as appropriate, so that it's a static data which is going to be static for, let's say, 5 minutes or so, and then you can consistently keep updating the CDN.
Okay.
Right?
All right. Sounds
Yeah,
good. And
cool.
what indexing strategies would you employ for this backend? Like, how do these indices impact query performance?
Sure thing. Yeah, definitely. So, as we are talking about this time series database, so let me give you a rough metadata of this particular table. So, let's say we have historical weather. That's what we are talking about as a past weather. And then let's assume that every row will have an ID, which is a primary key, and then we have a location ID. Let's assume that we are mapping different locations as an internal location ID, so that in the case of a location got split later point of the time, we are not, I mean, we're not really need to make a lot of changes. Rather, a new location ID will be generated for a split location, and the old one will work as it is, and the new ones will provide even more detailed data. And then let's say every historical weather, we have a date and as well as timestamp. Let's assume that even in this particular one, we have granularity we can think of, where if it is within the week, you have more granular information like hourly information. And if it is more than a week older, then we have either daily information, which is aggregated and then kept in the database. And the different data points which we talked about is temperature, humidity, and then the other details which we talked about, air quality, and so on and so forth. And then also we want to keep some housekeeping information like created time, created it, let's say. And then if we want to also capture some information like in a historical, some events or some relevant information where any weather event or so, if this also can be captured along with that. And
Mm.
when looking at this, what are the different usage patterns for from the user's point of view? Usually, they want to know the historical weather for a specific location. So, obviously we want to make sure that we index the location ID. So I am putting it as index, and also they would be looking at a specific dates, and in this case we would actually index this. But usually what happens is you're taking a location and a date combination. So in this case, like instead of indexing location and date independently, we can think of having a composite key of that.
Hmm.
Right, composite key of location and place date. That will actually help us quite a bit. I'm putting the bottom just for ease of reading. Yeah. So these are the things which we can actually look at. And if, let's say, this application is supporting something like where's the hottest place in the last 1 day or so, if those kind of queries are coming in, then it's always good to index based on those things. But it's not common. So depending upon what kind of application use cases are present, we would be providing some indexes. And these are the indexes which you need to be cautious, especially because uh, these indexes can actually bloat up the database space and also increase the time to insert or update or deletes as well. So
Yeah.
it should be always uh, taken with a caution, I would say. The one option is to do the profiling. So database profiling is a concept where you would gather some key metrics when these specific use cases are being executed, and you understand where is the stress or where is the which particular queries are taking quite a lot of time, and then based on that, you can add relevant indexes or optimizations.
Yeah. Okay.
So, yeah.
Sounds good.
And I think we have a few minutes left. So one other thing which I can focus on is like API design. So in this case, what we are talking about is users requesting the data from the weather service, and these are three different weather services or internal services which we have, which are providing the data. So we can think of like, since it is request response format which we are talking about, so we can build them as a RESTful service and RESTful API. So we would be getting generally the get requests are the ones which we are getting for this particular one, and the ingestion could directly put into time series database. So and from AWS IoT, this will be like a put or post depending upon things how we design. And few things to keep in mind is, as we are building this application, make sure that you follow the right RESTful API development mechanism. So it's something like making sure that you have right versioning. In this case, like let's say we are talking about get today weather, and then location uh, is the ID which you are taking. That's it.
Hmm.
And then let's say if you have to make some changes instead of location as a location ID, if you're thinking of adding some additional features like a county you want to get and which is not present, so then still what you could do is like you can add new APIs. So it's still V1 and today, and then county is something which you could use. Along with the location, if it is you're giving it as a unique ID, but later you want to support additional thing which is like longitude and latitude, and then you have internal service which will convert that. So in that case, like it's always good to add a different version of the API so that the new users would be able to accommodate that, and old users who are using that API will continue to get the service as it is.
Got it. How would you ensure API security?
Yeah, API security, there are multiple ways you can do that. So the first thing is to make sure that you have the handshake which is happening between the front end and back end. And in this case, we have front end which is internal to this system. That's how we are assuming. So the kind of security protocols will be comparatively lesser, I would say. So depending upon how you build it, but if they are using the public APIs, then you want to make sure that every time you establish a session and then you provide a session token for
Yeah.
every request. And that's quite critical because let's say if you are using the public APIs, not just our front end, but also somebody like Apple would like to use this service in order to provide their weather
Yeah.
information, then you should be able to understand the usage and use cases, as well as you should be able to throttle if one user or one particular organization is bombarding this service quite a bit. So
Yeah.
all of these will be possible when you add something like an API gateway in front of your load balancer, and then all of these requests are going through your API gateway, and the session token will help quite a bit.
Okay, got it. What if, let's say hypothetically, there's a huge weather event and there's a surge of potentially data that you're getting from your sensors. Can your system handle that load, and what changes would you make, if any, to your system to make sure that you can handle scaling in that sense?
That's a great question. So we have been focusing on the user side of it, but let's say sensors have been either malfunctioning or publishing a lot of data. We assume that it's publishing every 5 minutes. But what if, as you said, there's a weather event and it's publishing the events quite fast or so? So in that case, like instead of thinking of AWS IoT to ingestion as a post service, rather I would introduce a different component in between. So it's basically we can use a queue. It could be a Kafka or so, a message broker we can add, and then this will support, or at least this will help us streamline the incoming request and not to overwhelm the ingestion service. And whenever you can have some different metrics on this, how many messages are in the queue at any point of the time, and then if you see ever increasing trend and then your ingestion service is not able to cope up with that, then you'll be able to scale immediately according to that. You can also employ some auto scaling rules as well based on the number of requests that are waiting in the Kafka queue.
Got it. Okay, this is a good place to stop. Thank you so much, Suman.
Yeah, thank you.
Would you like to share any thoughts about this interview? Any advice regarding questions like these that people might encounter in the wild?
Yeah, definitely. So one of the thing is like for system design for the weather application or so, it takes weeks or even months to come up with designs and iterations. So nobody expects you to come up with a perfect solution within this 30 minutes. So always practice, think about why you're adding a specific component. It's not just adding a cache or so, but you should have a need for that. So make sure that you can justify any component which you are breaking down, or it could be possible that you are combining them if the system is having very high latency, and then combining a couple of small microservices could actually reduce the network load or network delays and stuff like that. So always think about the reasoning is the most important aspect. As an interviewer, I would not look for like, do you know XYZ technology? It's rather, what is your reasoning? Because technology keeps changing and you
Yeah,
should be catching up quite a bit, of course.
yeah, exactly. So, I mean, you don't have to know the latest and the biggest and baddest technologies out there, but if you know the concepts, that's what someone is looking for.
Exactly. Yeah.
Um, Thank you so much, Suman. Good luck, everyone, with your future interviews, and hopefully we'll see you around again.
Well, thank you.